Ladies and gentlemen, I'm going to start the introduction on the grounds that tech can catch up. I'm very sorry that this panel is late. But it's probably the latest we've ever been.
Time travel.
As you are probably aware, there are two types of matter in the universe. There's baryonic matter, that's Barry over there.
What? Hey who? Oh, and doesn't matter.
That's called dark matter because you're all in the dark. But this is all going to be explained to us by Dr. Martin Lavalle of the Maths Department of Philippine Research, right? Thank you very much.
Hooray!
Thank you very much for the invitation. And I spoke here once quite a few years ago, and I was totally traumatized at the end of it because I was trying to do a scientific experiment, and it involved a really difficult task of popping a balloon. And I ended up having to stab the thing to get it to pop, and it didn't pop. Anyway, so now we're having a little bit of technical trouble, but if not, it just means we can't see a couple of videos. And I'll try and find them on the internet and send a link to Gary to put up somewhere. Okay, so we know roughly what matter is. It's things like this. You all know what antimatter is. There's drives in NASA and so on. Dark matter is a little bit weirder sounding. Dark energy is weirder again. So what is the matter with the universe? And what I'm going to try to do is just give an inkling of why people think that dark matter must be out there, and a tinier inkling of dark energy. Okay, so we all use the scientific method, and people who are writing hardcore science fiction use the scientific method. And when you look into the night sky, you see things and you say, okay, well, we have a theory based on it. And that's using science, and we're trying to understand what it is that we see. So, that's the sort of thing if you've got alien eyes that you might see when you look into the night sky. And there's lots of stars out there, and you can try to observe them, and you get the fixed stars, and you get things that wander like planets. And so I guess every society that's done this has looked at the night sky and tried to understand what's happening. And going back to the ancient Babylonians, the Greeks, and everyone. One of the things that you see is this thing called apparent retrograde motion of the planets. So this is sadly not an invasion fleet, but repeated images of a planet, and it seems to be going along and then moves backwards and then carries on going. So this is called retrograde. It's going backwards, and it's actually apparent because it isn't really happening. It's really going that way, or it's going that way. I don't know which direction the photograph is. And this caused a big puzzle to people who are trying to understand cosmology and trying to understand the world around us. And so they built up models trying to understand the motion of planets. And although some of the ancient Greeks did suggest that you'd have the sun at the center of the solar system with the Earth moving around it, there were people like that. The one that was most popular was based on the idea that right in the middle we have the Earth. And, that makes a lot of sense in a way. I mean, if you think about it, if you drop something, it falls towards the Earth. It doesn't fall towards the sun or anything like that. So people thought it's much more sensible that we put the Earth in the middle, and then if you want to try to get this apparent retrograde motion of the planets in, you've got to give them these very complicated little orbits, and terrifyingly complicated if you ask me. And the person whom we associate with this is primarily, I suppose, is Ptolemy. And he had a model, a theoretical model of how the solar system is formed. The Earth is at the middle, geocentric, and everything else is going around it in orbits, and you've got the stars that are on the outside. And with this, he was able to more or less explain what's going on. Another reason, by the way, for why the Earth, for why the Earth should be at the centre is if you say that you've got the sun at the centre and you've got the Earth going around it, well, I mean, you know, surely we're going to notice this huge wind, everything being blown away. And this was definitely one of the issues that, you know, the Greeks and the ancients had. You know, so no, we're going to be geocentric, and everything else is going to go around us, and everything falls to the Earth, and the Earth is stationary. And, you know, there's a bit of wind sometimes, like this afternoon, but, you know, it's not that everything is being blown around as it goes into huge fast orbits. And of course it doesn't work. It doesn't explain things. So you start making life more complicated. So you start, and I don't want to go through the gory details of this, but you know, you introduce this keyword here, epicycle, which is you say, well, on top of our cycle, you've got the Earth somewhere in the middle, and you've got some sort of planet going around, and it's on a circle centered on another circle. This is an epicycle. And if that doesn't quite work, well, it's obvious what you're going to do, isn't it? You're going to put an epicycle on an epicycle. And people did do this. And you also get circles that are offset a bit from the main, and there's lots of Greek words for what all of these things are called, but you know, let's not worry too much about it. But it was really complicated, but it worked. Now we're going to see whether this works or not. So let's see if this video works, and if not, I can describe it to you, which will be almost as good, but not quite. No, it doesn't look like it's going to play. No, it's asking about this Adobe Flash player. Okay, so take my word for it. You can do anything with epicycles. And if you want to, if you have enough of them, this video shows 50 of them. So you've got, you know, the Earth at the middle, you've got a circular orbit, and then you've got an epicycle, and another epicycle, and then you choose the speeds of the Earth, of the different circles as they rotate, so it's wheels on wheels. You too can draw out an orbit which looks exactly like a painting or a drawing of Homer Simpson. And that's true.
Well, it reminds me of a spirograph, isn't it?
It's very much like that sort of thing, exactly. And what you would do is you plan, you take your drawing, and then you would mathematically work out what are the sets of wheels you need, and then you do it. You turn, and then you just turn the handle around. It's exactly like that. Okay.
Take the video of Mike play. Oh. The Acrobat Reader is installed now.
Let's have a go. Thank you.
It may play.
Anybody wants to see it?
It's got flash on it.
I can show it to them afterwards if anybody wants to see it. Okay. So, so the geocentric one was the one that worked. It was the one that churches liked because it had the sanctity of being viewed as a good thing by the ancients. And then Copernicus, shown here, came along, and Copernicus produced a theoretical model that was heliocentric. The sun is in the middle, and he wrote a couple of books, and it's a short one that was just circulated with a few friends, and a bigger one, which was basically the last thing he saw before he died. So he produces this book, and then it went out, and a lot of people said, no, really don't like it, and so on, this is wrong. But there were some people who thought, I like it, this is how we should be trying to describe things. And you can see in a solar model how you're going to get this apparent retrograde motion. So there's the sun, this is, let's say it's the Earth, and this is another planet, let's say it's Mars. And you're looking that way, and you say it's there compared to the stars. And then, you know, as they both go around, you see the other planet is there. And then as you go around a bit later, you see it's there. So you've gone from 1 to 2 to 3, you know, you're going backwards, and then 4 is here, and then a bit later on 5 is there. So by tuning these speeds, you can produce retrograde motion. And this is what is seen in reality. And Copernicus was not believed at the time. I mean, you've got quotes from people like Martin Luther saying this is utter nonsense and so on and so forth. Now, around this time, there was a Danish gentleman who had an amazing moustache, and he also had an awful lot of money. So I'm not quite sure how you pronounce it, because my Danish is non-existent, but let's say he's Tycho Brahe. He was given by the Danish king 5% of the Danish state's money to spend on research. So, I mean, I don't think any state has ever spent as much on science as under this one king in Denmark. And Tycho Brahe was just before the telescope. So he did all of his astronomy with sextants and devices like that. And he had this castle, Oranienburg, on an island, and he was not apparently beloved of the peasants because he was sort of putting taxes on them and making them work to dig things and so on. And in this castle he had apparently utterly wild parties, very much debauched, and as well as that, he had research. So he would be doing, as I say, no signs of telescopes, measurements. A friend of mine has been to where it was. And so first of all, he realized there could be vibrations. So he had this big pit dug down to the bedrock, so it was much more solid. And then he would be trying to measure things, angles and so on. But he then couldn't write things down because to do that he would needed a candle and light. So he was telling servants who were then going away and then telling another servant that things were being written down at a distance. So he produced amazing data, which was better than anybody else did ever before the telescope. Okay, and then, I mean, what's the worst thing that could happen to Tycho Brahe? Well, yes, that later. The King of Denmark dies. So the King of Denmark dies, and the next king doesn't want to spend as much on science. So he ends up leaving Denmark. All of his stuff was built in such a way that that he could take it to bits and pack it. And he went down to the Holy Roman Empire and became the imperial mathematician, which is a cool sounding title. And around there, so these are names of Holy Roman emperors, the Rudolphine tables. He got a new assistant, Johannes Kepler, and they worked together. Now, I don't know about you, but when I was much younger, I remember hearing this rumor that Kepler might have been involved in murdering Tycho Brahe to get his position. I don't know if you've ever heard that. Well, apparently, more recently, they've actually dug Brahe up out of the ground and taken things like beard hairs and so on, and there's no trace of poison in them. So, it's nice to think that there's no truth in that. Okay, so Kepler comes on the scene now. Brahe dies, unfortunately, and Kepler, who looks, if you look at that picture, like a fairly modern person, doesn't he? You can imagine relating to that. But he's got this nice collar on which shows he's got some money and so on, so he can keep it clean. But Kepler's mother was put on trial for witchcraft, and Kepler had to spend quite some time trying to defend her. So, this is all taking place in a really different society to the one we live in nowadays. So Kepler worked on using Brahe's data to understand what's going on. And what he really wanted to do is he wanted to prove Copernicus's theory that we have the sun at the center with the earth going around it. And Tycho Brahe himself had a theory where all the planets went around the sun, but the sun went around the earth. But Kepler actually wanted to go for the full Copernican theory. And so he had to work. And he worked doing calculations using Brahe's data, and obviously he had to do other things as well, but it took him 8 years. 8 years of work, you know, books and books of calculations until he was able to explain the orbits of the planets. And the first thing he sees is the path of the planets about the sun are elliptical in shape. So the sun is at the focus of an ellipse. You might remember how to draw an ellipse. So you take 2 points, you call them the foci, you put a loop of string around them, and you put a pen in the loop, so it comes here, say, and then as you move it around, the string doesn't stretch, its length is there, and then here, and here, and as you move it around, it's here to here, it's the same length, and that draws out an ellipse for you. And so that's his first huge thing. And people who looked at Kepler's work said, no, ellipses. Ellipses aren't right. Circles are perfect. God created a perfect universe. It must be circles. And, you know, so it's going to be a circle with a circular epicycle, surely. But if you do that, you know, it's not an ellipse immediately. You need lots of them. Okay, so that's the first thing. We have elliptical orbits, which was shocking to his contemporaries. The next thing is, as it goes around, if you imagine just, you know, the planet's here, it goes to here in some time. If you imagine shading that area, and then later on, when the planet's a bit nearer to the sun, during the same time period, so let's say that's a day or a week or whatever, day or a week, whatever, you shade in that area, and that area will be the same if that was the same amount of time. So that's one of Kepler's laws of planetary motion. And if you think about it, what that tells you is, if you're further away from the sun, you are moving more slowly than if you are nearer. Okay? Because if you're further and you're moving slowly, you may not move this far there, but you've got this big long length to make the area bigger. And that's going to be a really important thing for dark matter. Okay? That idea is really important. And then Kepler was able to go further and say this, that the ratio of the squares of the periods of a planet is what its year. How long does it take for it to get around the sun once? That's the square length. It's equal to the ratio of the cubes of their average distances from the sun. So let's just look at this. If you look at the Earth, it takes 1 year to go around the sun. Surprise. Its average distance in astronomical units is 1. It's the definition of an astronomical unit. And if you square that and divide it by that cube, well, 1 squared over 1 cubed is 1. Look at Mercury. It's much closer to the sun, so the average distance is much less. And a year for Mercury is much less than an Earth year. If you take that squared, divide it by that cube, you get very close to 1. All of the planets, you get very close to 1. So, as you move further away from the sun, it takes a longer time to get around the sun. And we can look at that a little bit more in a minute or two. But if you just look at that last column, all those numbers so close to 1, and that's, you know, something that people can really predict. Okay. So we have Kepler. Now Kepler's stuff is all just based on data. There is no fundamental law. This is Blake struggling with Newton, trying to work things out. And Newton produced a universal law of gravity, and Kepler's laws, everything, the ellipses, the type, the areas, all of that just drops out if you solve Newton's universal law of gravity. All of these things come out of it. So Newton did this huge, amazing thing that people were utterly in love with. Okay. So, gravity is a law. There is a theory which explains everything. So this is the sort of thing that theoretical scientists like myself really like. Oops. not trying to print anything. So we have this nice law, and the law explains everything. And that law lasted for a long time, and then of course Einstein comes along, 1915, theory of general relativity, and you've probably seen pictures like this before, some sort of curved space-time, curvature caused by big mass, and this explains things like the planets, satellites, everything. And John Wheeler, apologies for this thing being slightly on top of it, he tried to describe general relativity in the following way. Matter tells space how to curve, so you've got something big and heavy like a planet, and it curves space, so it's like having a sheet and dropping a weight in it. And then if you imagine rolling a marble on that sheet, its path will not be a straight line, it will be curved because of the curvature of the sheet. So space tells matter how to move. Okay. And this produces an effect that was a big surprise for people. Light bends under strong gravity. So if you imagine you've got a star here, and light comes from it, and comes near something heavy, like say the sun, it can be bent around, changes direction, and it comes to the Earth, and we see it here. And if you're looking into your telescope and you see the light coming in here, of course what you think is, well, the light came from there and the star is over there. But it wasn't. So we have this prediction that light doesn't follow straight lines, it bends under gravity. And this was a definite prediction of Einstein's, and of course 1915 got the First World War going on, so people were doing a lot of other things, but there was a pacifist scientist called Eddington in Britain. Eddington didn't want to be involved in the war at all, and the Astronomer Royal said to the British government, well, Eddington can do something really useful. He can go out and set up an exhibition for when we have the next total eclipse of the sun, and then we'll be able to see light that's been bent because it's come from the star, it's come very close to the sun, and because that will be covered in darkness, we'll be able to see where the stars are. Okay, does that make sense? Okay, and then because this is during wartime, and to make the government sort of sympathetic to them, they say, and by the way, what he's going to do is he's going to show that this German nonsense of Einstein's isn't true, and what is true is the old British theory of Newton. Now, the Astronomer Royal who said that didn't believe a word of what he was saying. He actually thought Einstein was right, but he thought he'd get the politicians on his side by saying something like that. So out they go in 1919, having prepared for a few years. And this is a negative of an image, so this bit would be really dark, it's where the sun would be. There's dark patches where the light is coming around. And then you've got the light images, if you look carefully, of some stars. They went to two places to look for it. They went to Brazil and they went to an island off the west coast of Africa, different scientists, obviously. And they did that because they're scared of having something that we had. Do you remember the last transit of Venus in Plymouth? Do you remember the nice cloud cover that we had? So they're worried about that as well. And one of the two places, Africa, I think almost every photo they took was useless because of wispy cloud getting in the way. But there was one very good photo from Africa, and there were more photographs from Brazil. So they were able to show that Einstein's theory works and this bending of light happens. And then Einstein made a prediction which he put in print in 1936, saying that gravity can act as what's called a gravitational lens. So again, you've got some source here of light. Light's going out of it in different directions. It goes past stuff that's really heavy, and the light gets curved, and you might see multiple different images of light, of the same thing. So that was a prediction of Einstein's. He was initially thinking that this could just be, the heavy thing in the middle might be a star, but that was a very difficult thing to actually see. The change is going to be very small. And then somebody called Fritz Zwicky said, well, actually, what about if you've got galaxies in the middle that can produce a really big bending effect? And it was first seen in 1979, okay? So 43 years later. And this is it. These two things here are quasars. They're really powerful, bright things at the heart of the galaxy. And they're actually the same. So you take the light, you put them through different devices. So that means you're trying to see how much blue light is there, how much green light is there, the different wavelengths, etc. And all galaxies are going to have a slightly different fingerprint. Those two are identical. So it's actually the same thing, and the light has come in two different routes to reach the telescope, and that's how they see that. So that's galactic lensing. In the meantime, people have been able to see this many more times. I've just zoomed in on that image there. You can find images where you've got one galaxy and the light from it is appearing in as 4 different copies and so on. Okay, so by the way, just you might know this already, but general relativity, if you came here using your phone and the map on it, your phone uses special and general relativity for the GPS system. And if you didn't use that, your position on your phone map would be wrong in terms of kilometers. So it would be utterly useless for finding the hotel. But you don't need general relativity for galactic rotation and solar rotation. If you look at the Earth, at our solar system, the only thing that you need Einstein's theory for, really, in our solar system, is the behavior of Mercury. Because that's really close to the sun, so you've got really strong gravity there. Everything else, we can just use Newtonian theories, and it will be enough. Okay. So, let's go back to Kepler. Don't worry, it's not much. Kepler tells us that the average distance from the sun and the average time to go around the sun once squared, so that's cubed, and that squared is 1. Speed is distance over time, and if you take that and combine them, what you get is that the speed of a planet going around the sun should go as 1 over the square root of the planet. So that means if you increase your distance by a factor of 4, the square root of 4 is 2, your speed will be halved. So as you go further and further away, that's what happens.
Have you been able to test this for other galaxies?
You've been watching this, you've been sneaking into the slides. It's a very good question. It's a very good question. It's a very good question. Your name is Vera Rubin. So this is it for our planet, our solar system. So we just said it goes as 1 over the square root. The dots is the data for the planets of the solar system. Pluto is there, whether you're going to call it a planet or not, it still obeys gravity. And the line is 1 over a square root there. So it works beautifully. So Newton's law of gravity predicts this, and it's seen in the data. So at this stage, we'll just check. If you see I'm not even seeing the mouse. Okay, so Vera Rubin was an astronomer. She had 4 children. She didn't want to spend all of her time traveling away, leaving her family, so she wanted to find something she could do being based where she was in California, I think it was. No, sorry, it's the East Coast. Anyway, and she thought she'd do exactly what you're suggesting. She was going to try to look at rotation curves inside galaxies, so the nearest one being the Andromeda galaxy. And what she found is totally different. So here's roughly what she sees. What you would expect would be a curve like this, and what you find is in the middle of the galaxy, you don't really see anything like that at all. But in the middle of the galaxy, it's not that in a galaxy all the matter is in the middle, but certainly as you're away from there, you should be seeing the big mass at the center of the galaxy, and you should be getting this, and you get that. In the meantime, by the way, they have found a galaxy where it does behave that way. Only one. And they don't understand that either. That's really weird. People have theories. Theorists have theories. But, there's one. But all the others, as far as I'm aware, it's like this. So this is not agreeing with Newtonian gravity. And it's not that using general relativity would fix it. It wouldn't. So what people say is, if gravity isn't working, it must be that there is some other matter we can see, which is in this galaxy, and that this is changing the predictions. And we can't see it, so it's not shiny like stars or planets that reflect light. So we're going to call it dark matter. And there are basically two theories for dark matter. Theory one is you've got some very heavy objects which are very cold and they don't shine. I mean, you and I, we've all seen this in, I don't know, Predator, that we're all lit up because we're radiating in the infrared. So presumably it could be large-ish, but not too large, but heavy-ish objects that are out there, and they're producing this effect. And because people are often a bit silly, they've got a silly name, they're called machos. Massive, compact, halo objects. The other possibility is called WIMPs, again silly names, and that's weakly interacting massive particles.
Excuse me, do scientists spend a lot of time coming up with the names so they make silly acronyms?
I am absolutely certain of it. If you think about quarks, up, down, okay, well, why not? Strange, beauty, charm, top, bottom, truth and beauty, but most people say top and bottom now. That's a bit weird.
Boring.
Yeah, but no, people do. You definitely, I mean, I know somebody who wrote a paper on quantum teleportation, and he's a professor at Cambridge nowadays, and that paper got loads of publicity. But if it wasn't called quantum teleportation, it would have got less recognition. I mean, it's still a lovely thing, but people
Is that using the entanglement?
Yeah. To make a copy of something and then destroy the original. So you get into the device, a copy of you is made somewhere, and the big grinding thing comes down and destroys you. I'm not sure I would want to be transported. Not that way anyway. But okay. So this is the main evidence for dark matter. Galactic rotation curves, and it just shows that you cannot explain the rotation of galaxies from Newtonian gravity. But there is other evidence as well. So we have this device here, the Holmdel Horn antenna, and there were two people, Penzias and Wilson, who were both physicists who had done PhDs in radio astronomy. And then they went to work for Bell Labs, and they were actually producing a device for looking at communications. And of course, this communication device using microwaves, this was much bigger technology than we probably have nowadays, but radio telescopes still, you want them to be big. Just to show you, by the way, what they actually were communicating with, they actually had satellites that they were bouncing things off. And so let me show you a picture of a satellite. This one is from about 1960, I think.
Echo 1.
That's a car. It's a balloon, and it's a balloon covered in some sort of metallic reflecting stuff, and it got floated up to a height of about 1,000 miles. How they managed to control the air so that it got to the right thing, I don't know. A lot of very hard work, I'm sure. So that was the Echo communication satellites, and they built about 2 or 3, I think. So Penzias and Wilson started seeing this slightly weird small signal because they were testing their device. And one of the ways you test a device is you just point it somewhere where there's nothing. So you aim it into space where there's no galaxies in that direction, in the near vicinity, nothing's producing lots of radio waves. You don't expect to see anything, they got a small signal. And it turns out other people had seen this before them. And everybody else who'd seen it before them thought, oh, there's a bit of a glitch with the kit, but it still works, who cares? But Penzias and Wilson spent a huge amount of effort trying to get rid of this little glitch. There were some pigeons nesting in it. They took them 50 miles away and cleaning out the pigeon crap. They thought that might be the cause, etc., etc. In the end, they actually ended up ringing the university department and say, look, we think we've got this signal, we don't know what it is, but it seems to be everywhere. And people who've been looking at the Big Bang said, we actually think after the Big Bang there should be some sort of afterglow of the Big Bang, this cosmic microwave background. And nobody's ever seen it. We're talking about building experiments to look for it. Oh, you found it. One of the top physicists said we've been scooped when he heard about it, and these two guys got the Nobel Prize in 1969, I think, for what they did. And the key lesson for all of us is that other people had seen it before, but they just thought, oh, it's some little thing, I'm not going to worry about it, and they took it seriously and tried to find out how to get rid of it, and then they realised they couldn't. Okay, so cosmic microwave background, you've got lots of different sorts of electromagnetic radiation, light, infrared radiation, we're all radiating radio, gamma rays, all of these things. So you've got different frequencies, and you've got how much is radiated by empty space, and this is what you get, and this is what's called the cosmic microwave background. It shows that the universe is shining at an incredibly low temperature of about roughly minus 270 degrees C. And this is actually something, this would be a completely different talk. This thing, the idea of a black body spectrum, is actually the very beginning of quantum mechanics. Max Planck, back in 1901, was able to explain this curve by introducing a theory that turned into quantum theory. And the cosmic microwave background is actually the best fit to Max Planck's equation of any spectrum. So it's really, really lovely. And nowadays, of course, they don't use the Penzias-Wilson kit. They tend to put satellites out in space, and they look to see what's going on. And this was Kobe, that you may remember, and this is the cosmic microwave background. You get slight variations. These slight variations are nowadays thought to be related to things like matter and dark matter behaving slightly differently. Because if you imagine there's a lot of light just after the Big Bang, and the light's presumably not interacting with dark matter, so it's going to behave a bit differently. I mean, this is stuff that is not understood.
Sorry, what are we looking at here?
We're looking at you're just looking out into the universe. Now, if you look at a raw picture, you would have a line across the middle, which is the Milky Way, so that's been removed. You've also got lots of dust from our galaxy, that's been removed. And then you're just looking at essentially empty space, and it's radiating at the temperature that is left after the explosion of the Big Bang has cooled down to nowadays. So if you look into the far distances of space, empty space, it is radiating. Just as you are radiating, but at a much, much lower temperature.
What's the difference between the green and the dark blue?
Well, that's slightly different temperatures. So it's slightly different patterns, and that's thought to be to do with how how matter and dark matter and so on have behaved. And after COVID, they sent out, WMAP, and that's a better image. So that was slightly older technology, although it's not that long ago. Better technology, you're getting a less blurred image. And again, you see these structures. And trying to understand these structures is a thing a lot of cosmologists spend a lot of time on. And the patterns show that there's got to be dark matter, and there's also got to be dark energy. Now, dark energy, I've just tried to describe in the following way. One of the things you really want to have, if you are an astronomer, is a standard candle. So you want something which burns with a set brightness. So if you see it and it's very bright, you know it's near to you. And if you see it and it's not very bright, you know it's further away. And there is a type of supernova which they believe is a standard candle. And you look at that, and with it you can try to work out how the universe is expanding. And what those measurements seem to show is that as you go further away, the universe appears to be expanding, if anything, more rapidly. So what you would expect, naively, is you've got gravity. So, I mean, between gravity, you and I, there is a force between us pulling us together. There's a force between you pulling us together, you together. So you'd expect it to be slowing down a bit, but the actual data seems to show that it's expanding. So what does that mean? Well, we say there is something else out there. We don't know what it is. We call it dark energy. Dark because we can't see it with light. And it is somehow causing the universe to accelerate, to expand more rapidly. How it does it, there are hundreds of papers out on the archive. But, nobody really knows. So, the European Space Agency sent up the Planck Space Observatory in 2009, and they didn't go backwards in time to 213 AD, it went out to 2013, a bit more time travel there. And what it seems to be is that the matter that we know about, baryonic matter, etc., is only about 5% of the universe. I mean, this is what they thought before Planck, this is after. Dark matter is about a third, and dark energy, whatever that is about 2/3. So we don't know very much. We really don't. Now, if you look at CERN, the Large Hadron Collider, it's looking at very different scales. It's looking at things happening in short distance scales, and that works really well. If anything, and that's more my area really, I'm a particle physicist. If anything, the big problem in particle physics is that we've got this ugly standard model that describes everything. Everything works. And what you would really want is something that doesn't work from the experiments. With cosmology, you've got the opposite problem. You've got loads of things you just really don't understand. But we've only got the one universe, so it's a bit difficult to do lots of experiments and so on. So, just thinking about ordinary matter, these are the quarks. These are the leptons, the electron and its heavier partners. These are the neutrinos that go with them. And so these things, called fermions, this basically, to a first approximation, we've been built out of these. This stuff, there's some of it around us, but it's not as important. Actually, no, we're built out of this. And then we've got the particles that interact between them. So, for example, electromagnetism, there's some over there for the raffle. I saw that there is some levitation kits. You've got magnetism. So you've got charges, but you've also got photons, which produce that interaction. And for quarks, you've got gluons. For the weak nuclear interaction, W's and Z's. The Higgs has been discovered recently, helps in producing the masses. So all of that stuff we understand. It's just, doesn't it remind you a little bit of epicycles? There are far too many of these things. We'd like it to be simpler. Yeah, Yeah, we're still in the I mean, the difference is these things exist, but you'd like to think they're made out of something simpler, and you would love the LHC to give us some data. And then, you know, we've got all of these different forces: electromagnetism. James Clerk Maxwell, the first unified theory of science. He produced a theory that explained electricity and magnetism, electromagnetism. That was the first unified theory in all the physics, really. And then you've got the strong nuclear force holds the proton together, the weak nuclear force gives you radioactivity. But we haven't got gravity. And gravity is outside of this. So all of these particles have masses, that's the charge of gravity. The thing like a photon is supposed to be the graviton, but we don't have a quantum theory of gravity. There's no quantum theory of gravity. You can write one down, but it's got lots of infinities in it. And quantum field theory's got lots of infinities, but you can normally get rid of them in a well-defined way. Gravity, we don't know how to. So that's why people try to produce things like string theory. They say, we'll have a theory of gravity through strings, which we can sort the infinities out. I don't think they can yet, but that's a person with the. So basically, I think if you look into space, we have big problems. In the ground, under the Earth, in the LHC, everything works too beautifully. In space, we have absolutely no idea. There's loads of weird stuff out there. So we really don't know gravity that well. We don't have a quantum theory, but the quantum theory, having a quantum theory would not fix dark matter. You don't need a quantum theory of gravity to describe galactic rotations, in the same way that you don't need to use quantum mechanics to describe the path of this pencil through the air if I throw it. You can explain that with classical science. So the same would be true of galactic rotations. But it is still possible that all of this dark matter and dark energy stuff is maybe not true. It is I'd say it's definitely a minority view, but there is this idea called MOND, modified Newtonian dynamics. And the idea is that you've got Newton's theory of gravity, but if you're looking at very small accelerations, the force changes. It's not quite the force we have. Now, is that an epicycle? Or is that a deeply insightful view into the future? Nobody knows. The majority of physicists, I would say that the large majority of physicists are not keen on that, but there is a minority. I have met people who are keen on that. So there are lots of problems out there. The problem with this image is the problems are up in the sky, but the sky is also below us, a long way down. The theorists have loads of solutions. I'll tell you a joke. Which I think is quite true. There's a theorist, and she meets an experimentalist. And the experimentalist shows them the data, and the theorist goes, "Oh, that's wonderful! It really, oh, that's great! My theory is going to be so good for that." And then the experimentalist goes, "Oh, hang on, sorry, I made a mistake." Grabs upside down. And the theorist goes, "Even better." So. I don't want to completely do down my area because, theoretical physics I think is a wonderful thing, but there are loads of ideas out there. They're really wild, they're really strange, and we don't know what the answer is. I had a rucksack here, which I know.
Okay.
Is it? Oh, thank you. And I just sorry, being an academic, you always want people to read books. So if anybody wants to read something about that, I think this book by Simon Singh, who was a journalist, I think that's a very good book. Which, I think people who are interested in this can get a lot out of. So I'll leave it at the front if anyone wants to have a look at it. Sorry?
It's really
It is, isn't it?
how accessible is it?
How successful is what?
Accessible.
I think it's very accessible. The hardest thing in it is if you want to, it does a little bit of multiplying numbers together, powers of 10. But you can skip that, I would say. I mean, I think it's, I mean, yeah, I'm going to leave it lying there for people to look at. You know, I think it's very accessible and very enjoyable. Lots and lots of nice stories. Okay. So I think that's it really. I'm finished, and I can't explain what dark matter is. I can't explain what dark energy is. And there is a possibility, of course, that there isn't any dark matter either.
Yay!